Each lobe is 25,000 light-years tall, and the whole structure may be only a few million years old. Within the bubbles, extremely energetic electrons are interacting with lower energy light to create gamma rays, but right now, no one knows the source of these electrons. Are the bubbles remnants of a massive burst of star formation? Leftovers from an eruption by the supermassive black hole at our galaxy's center? Or did these forces work in tandem to produce them? Scientists aren't sure yet, but the more they learn about this amazing structure, the better we'll understand the Milky Way.
Nearly 1,000 years ago, people saw an exploding star, right here. This is the Crab Nebula, the wreckage of that event. For most X-ray astronomers, it's the brightest and steadiest beacon in the sky. But now they realize it's not as steady as they thought. Several orbiting X-ray observatories have seen unexpected variations. Most X-ray telescopes don't have sharp enough vision to make images. Instead, they detect the crab as a broad source. From 1999 to 2008, it brightened and faded by as much as 3.5% a year, and since 2008, it's faded by 7%. The gamma-ray burst monitor on NASA's Fermi satellite detected the decline, and Fermi also spotted 2 gamma-ray flares at even higher energies. What's going on? Scientists think the X-rays reveal processes deep within the nebula in a region powered by a rapidly spinning neutron star, the core of the star that blew up. This image from NASA's Chandra X-ray Observatory shows how complex this inner region is. But figuring out where the crab's long-term X-ray changes are taking place will require a new generation of hard X-ray telescopes. Once regarded as an unchanging standard, the Crab Nebula flickers from energy ultimately provided by a long-dead star. Most big galaxies contain big black holes. Not just big, supersized, with millions of times the sun's mass. Some of these black holes are actively devouring gas. This drives particle jets that can spew matter millions of light years into space, and it also makes the holes a source of penetrating, or hard, X-rays. At these energies, the sky glows in every direction, even far away from bright sources. Astronomers have long suspected that active supermassive black holes in galaxies were responsible, but they just couldn't find enough of them to account for the X-ray glow, especially the peak of the energy spectrum. Now, astronomers using NASA's SWIFT satellite confirm that a largely unseen population of black hole-powered galaxies is out there. There are so many that scientists say they might fully account for the cosmic X-ray background. What emission we detect from an active black hole is a function of how we see it, whether we're looking face-on and into one of its jets, or viewing it from the side through the disk of gas and dust that surrounds it. The brightest active black holes, which include quasars and blazars, are those we see face-on. But as the viewing angle increases, the surrounding disk absorbs increasing amounts of radiation. Astronomers have always assumed that many active galaxies were oriented edgewise to us, but because the disk of gas smothers most of their X-rays, these sideways black holes just weren't detected. And that's where SWIFT comes in. Since 2004, the satellite's Burst Alert telescope has been building up the largest, most sensitive X-ray map of the sky. Using these data, astronomers found that the most heavily absorbed galaxies create the energy peak in the cosmic X-ray background. What does it all mean? When the universe was about half its present age, about 7 billion years ago, galaxies crashed together more frequently, and these collisions produced gas-rich galaxies with heavily obscured black holes. The SWIFT survey shows that galaxy mergers helped activate these black holes by feeding them torrents of fresh gas. The new findings are consistent with the idea that the X-ray background peaked around this time, when our own galaxy was young and before our solar system was born. The Crab Nebula is one of the brightest sources of high-energy radiation in the sky. Little wonder, it's the expanding remains of an exploded star, a supernova seen in the year 1054. Recently, astronomers using satellites sensitive to the highest energy form of light, gamma rays, have observed incredible flares in the nebula that theorists are hard-pressed to explain. The supernova left behind a magnetized neutron star, a pulsar. It's about the size of Washington, D.C., but it spins 30 times a second. Each rotation sweeps a lighthouse-like beam past us, creating a pulse of electromagnetic energy detectable across the spectrum. Here's what the sky looks like in high-energy gamma rays. The pulsar in the Crab Nebula is among the brightest sources. As the pulsar spins, its powerful magnetic field causes particles to flow. These currents ultimately light up the nebula. But as bright as the pulsar is in gamma rays, it isn't the source of the flares. NASA's Fermi Gamma Ray Space Telescope can look in between the pulsar's brilliant pulses to reveal the faint gamma rays from the underlying nebula. Yet several times since 2009, enormous flares have erupted somewhere within the nebula. The most powerful one to date lasted 6 days and made the nebula 30 times brighter than normal and 5 times brighter than previous flares. During the huge flare, astronomers also studied the crab with NASA's Chandra X-ray Observatory. Chandra's keen X-ray eye saw lots of activity, but none of it seems correlated to the superflare. This hints that whatever's causing the flare is happening within about 1/3 of a light-year from the pulsar. And rapid changes in the rise and fall of gamma rays imply that the emission region is very small, comparable in size to our solar system. Scientists say the gamma rays most likely arise from electrons moving near the speed of light, which emit gamma rays as they interact with magnetic fields. But to account for these flares, the electrons must have the highest energies ever seen in cosmic sources, 100 times higher than can be achieved in the most powerful particle accelerators on Earth. Even after 1,000 years, the heart of this shattered star still offers scientists glimpses of staggering energies and cutting-edge science. High-mass binary systems are studies in extremes. They pair a hot, massive star with a compact remnant, like a white dwarf, a neutron star, or even a black hole, and they produce lots of X-rays. But only a few of these systems are known to emit gamma rays, the most energetic form of light. And only in one of them do scientists know the precise nature of the compact object. It's a pulsar, a neutron star roughly the size of Washington, D.C., that spins about 21 times a second. Each rotation sweeps a beam of radio emission toward Earth. Every few years, the system gets really interesting. That's when the pulsar's orbit carries it close to its massive companion star, which is surrounded by a disk of gas. As it swings around its companion, the pulsar twice grazes this disk, producing gamma rays each time. In late 2010, NASA's Fermi Gamma Ray Space Telescope watched the system glow with faint gamma emission as the pulsar first approached the disk. Astronomers expected the same behavior in early 2011 when the outbound pulsar grazed the disk again, but that's not what happened. Instead, Fermi detected intense and puzzling gamma ray flares. The system produced more emission on some days during the second pass than it did throughout the entire first pass. Yet telescopes observing at radio and X-ray wavelengths saw nothing unusual. It's a mystery astronomers are working to solve, but frustratingly, the pulsar is now heading toward the farthest part of its orbit. Better understanding this unique system will help scientists work out the natures of the compact objects in other high-mass binaries. Scientists will also use the data they've collected to predict what to expect at the pulsar's next close encounter in 2014.
Hi, I'm Elizabeth Hayes, a scientist working on NASA's Fermi Gamma Ray Space Telescope. Every 3 hours, the Large Area Telescope on board Fermi builds up a picture of the sky in gamma rays, the most energetic form of light. One thing it sees a lot of is blazars, active galaxies whose emissions are powered by supermassive black holes. Blazars are extremely active objects. Here's one of the most extreme Fermi has seen. It's been known to flare up so brightly that for a few days, it outshines every other gamma ray source. Considering that it's more than 7 billion light-years away, this is an immense energy output. At the core of an active galaxy is a supermassive black hole that powers jets of particles moving near the speed of light. We call it a blazar when one of the jets is pointed in our direction. This offers us the best view for seeing dramatic flares when there are changes along the jet. Fermi has found about 1,000 gamma-ray blazars so far. Every day, the gamma-ray sky changes, depending on which galaxies are in outburst and which are in a quiet phase. Because we're watching them all the time, we can track their activity and alert other telescopes to new flare-ups. As Fermi continues to watch the sky, it builds a more complete picture of the daily lives of these powerful objects. Some of the flares we see announce the presence of blazars we've never seen before. And sometimes we find a gamma-ray flare that is not from a blazar, which is very exciting. We hope to discover new types of gamma-ray emitting objects that we don't yet know about. Right now, nearly 1/3 of Fermi sources cannot be connected to any known type of gamma-ray source. Out there in the dark, what new discoveries await us?
Every day or two, on average, satellites detect a massive explosion somewhere in the sky. These are gamma-ray bursts, the brightest blasts in the universe. They're thought to be caused by jets of matter moving near the speed of light associated with the births of black holes. Gamma-ray bursts that last longer than 2 seconds are the most common and are thought to result from the death of a massive star. Shorter bursts prove much more elusive. In fact, even some of their basic properties were unknown until NASA's SWIFT satellite began work in 2004. Astronomers suspected that crashing neutron stars could explain short bursts. A neutron star is what remains when a star several times the mass of the Sun collapses and explodes. With more than the Sun's mass packed into a sphere less than 18 miles across, these objects are incredibly dense. Just a sugar cube-sized piece of neutron star can weigh as much as all the water in the Great Lakes. When two orbiting neutron stars collide, they merge and form a black hole, releasing enormous amounts of energy in the process. Armed with state-of-the-art supercomputer models, scientists have shown that colliding neutron stars can produce the energetic jet required for a gamma-ray burst. Earlier simulations demonstrated that mergers could make black holes. Others had shown that the high-speed particle jets needed to make a gamma-ray burst would continue if placed in the swirling wreckage of a recent merger. Now, the simulations reveal the middle step of the process, how the merging star's magnetic field organizes itself into outwardly directed components capable of forming a jet. The Damiana supercomputer at Germany's Max Planck Institute for Gravitational Physics needed 6 weeks to reveal the details of a process that unfolds in just 35 thousandths of a second. The new simulation shows two neutron stars merging to form a black hole surrounded by superhot plasma. On the left is a map of the density of the stars as they scramble their matter into a dense hot cloud of swirling debris. On the right is a map of the magnetic fields, with blue representing magnetic strength 1 billion times greater than the Sun's. The simulation shows the same disorderly behavior of the matter and magnetic fields. Both structures gradually become more organized, but what's important here is the white magnetic field. Amidst this incredible turmoil, the white field has taken on the character of a jet, although no matter is flowing through it when the simulation ends. Showing that chaotic magnetic fields suddenly become organized as jets provides scientists with the missing link. It confirms that merging neutron stars can indeed produce short gamma-ray bursts. At this moment, somewhere across the cosmos, it's about to happen again.
Roger the pitch. 7, 6, 5, Roger, 4, you're looking good. 3, 2.
We are the explorers. We have a need to find what is out there. It is a drive inside each and every one of us. The